Hi, Biochemistry. Welcome back to Chapter 18. We have talked through a lot of the review of stuff we talked about in the fall. We've also talked through a lot of the new stuff, what an electrochemical cell looks like and how it functions. So at this point in time, we're going to take a little bit of time and draw some relationships between some of these electrochemical concepts and some thermodynamic concepts. So we'll start out by looking at the relationships between cell potential, electrical work, and free energy. Now, before we get into this, I just want to give you a little disclaimer. We are talking through a lot of chemistry concepts that overlap with physics. And we're not taking the time to really define and understand these physics concepts. We're giving you a very light definition and kind of moving forward to look at the functionality of that definition. So if you feel a little bit confused through this section, that's okay. You probably should be, because these concepts in terms of physics are at least an entire unit, if not a couple units. And we're really blowing through the definitions to look at the application of those definitions in chemistry. So take this as a couple things. Take this as encouragement to take physics. Chemistry really is the central science. And having taken chemistry, you're going to understand a lot more in physics than if you hadn't taken chemistry. Also, by taking physics, you're going to understand a lot of these concepts in chemistry a lot better. The two classes go hand in hand really well, and you should take both at some point in time. The other thing is, as we talk through these things, you can understand them to the point that you need to for chemistry. And at the end, we're always going to kind of give you a punchline. So listen for those. What's really the takeaway here that you need to be able to run forward with and apply? Okay, so with that little caveat being said, let's talk about this stuff. Okay, so notice on the board I have this equation. Potential difference in volts is equal to work in joules divided by charge in coulombs. Okay, so we're going to talk about this equation for a little bit here, but really this explanation here is probably more important than the actual equation. So let's just take a minute and read through this and let it sink in. Let the meaning sink in here. So what this equation represents is that 1 joule of work is produced or required, depending on which way your reaction is going, when 1 coulomb of charge is transferred between 2 points in the circuit that differ by a potential of 1 volt. Okay, so this is what I'm talking about with these physics terms. So we just threw the term charge at you. We've talked about work a little bit before, right? Work is the ability to do something, whether that is move a box or climb a ladder or expand a gas or compress a gas. Work is required, right? In chemical terms, we think of work in terms usually of the energy released by a chemical reaction. So think about like eating an apple. Well, the chemical energy contained in that apple the energy in joules or calories of the apple, right, is put in your body, it's digested, your body pulls it apart, and then it absorbs the energy that's released when those bonds are broken. And then your body uses that energy coupled to the ADP, ATP cycle, right? The citric acid cycle and the Krebs cycle and all that good stuff. Your body uses that to do work, to go run, to jump, to complete all of your processes inside your body. So we measure energy in joules, and that in this case, energy is doing work. Now, remember, we've talked about energy before. Energy is work plus Q. Remember this? And Q for us kind of turned into the heat that's transferred. So remember, energy is never 100% work. 100% work will never actually happen, because all processes are going to lose some of the energy to heat. And when we talked about enthalpy, we talked about, well, if work is zero, and we made work zero by having a open container where there was no change in pressure, because remember, change in pressure was related to work, or change in volume was related to work. Okay, so anyway, we eliminated the work, and then all of the energy was then transferred as heat energy. Well, this is kind of doing the opposite. They're saying, all right, if we assume there's no heat loss, it's a perfect situation, then all the energy is going to be work done. Okay, so 1 joule of work is produced by your circuit. And then we talk about charge here. Now, again, we're not going to go super deep into charge, but you can think of charge as like the amount of electrons that are kind of shuffled through the circuit. So remember, if we have a circuit with a battery and a light bulb, it would probably look something like this. Well, we have a circuit too. We have a circuit that is divided and connected, and we can measure the volts that are running through our wire. So 1 coulomb of charge is transferred between 2 points in the circuit, probably this point and this point in the circuit. So 1 coulomb of charge is pushed through here. A certain number of electrons are pushed through that wire, and that's what we're talking about as charge. We're going to revisit this idea of charge in just a minute here, but that's kind of the idea of charge. And it's transferred between 2 points in the circuit that differ by a potential of 1 volt. So how do they differ by a potential of 1 volt? Well, remember, if we have one reaction here, let's see, whatever our reaction was, something like this. I think it was actually the opposite. Okay, so there's our reaction, and remember, they come with voltages for the half reaction. Then we add the voltages together, and we see what the difference in the potential is. Okay, so if 1 joule of work is produced when 1 coulomb of charge is transferred between the 2 points that differ by a potential of 1 volt. That's what this reaction is saying right here. Now, we can take the ones out of there and just make it an equation, and that's what we have down here. So the cell potential, that fancy E, is equal to work over charge, and we can calculate any of these variables when we're given the other two. One other note to see here is that work is viewed from the point of the system. It's from the viewpoint of the system. And so if work is flowing out of the system, that's going to be indicated by a minus sign. So notice there's a minus sign in this equation, and it's just, again, just like in the thermodynamic quantities that we talked about. Again, that minus sign is just talking about the direction of work. Is work being done on the system by the surroundings? Is work being done on the surroundings by the system, right? So that minus sign is only to indicate the direction of work being done. Okay, so knowing this equation, again, just a reminder, we kind of touched on this before, but in any real spontaneous process, some energy is always wasted. The actual work realized is always less than the calculated maximum. So if E is our calculated maximum amount of work that we can do, know that we're always going to do a little bit less than that work. So if we buy a 9-volt battery and we calculate the amount of work that can be done by that 9-volt battery, we know that we're not actually going to be able to plug that battery in and actually do that amount of work, because some work is always going to be lost in the system. If it's a spontaneous process, the entropy of the universe must increase, right? And so some energy must be wasted. And in an electrical circuit, that energy is going to be wasted in terms of friction of the electrons moving through the wire. Electrons moving through the wire are going to tend to make the wire hot. If you've ever worked with a computer on your lap, you have experienced this, right? That's energy wasted. And so as a result, we're not going to be able to do all the work, but we can still calculate the max amount of work theoretically possible to be done. So you don't really need to do a whole lot with that information. That's just kind of a caveat of let's not imagine this rosy view that's actually existing, right? Let's be realistic about what we're talking about here. But then we're going to move forward with these theoretical numbers and equations. Okay, so coming back to charge a little bit. So here we see that Q again, and this Q is the quantity of charge in coulombs transferred. And we can see that this is made up of moles of electrons. So again, we're talking about charge as the amount of electrons that are flowing through the wire, times F. Now, F is known as a Faraday, and F is just a constant. It's a constant that makes the equation work. So here's what a Faraday is. Faraday is 96,485 coulombs per 1 mole of electrons. So if you have 1 mole of electrons that flow through the wire, you will have 96,485 coulombs of charge that have moved through the wire, right? It is a proportion where the numerator and the denominator are equal. It is a constant, and it can be used as a conversion factor because the top is equivalent to the bottom, and so this proportion is equivalent to 1. I don't know what the symbol for equivalent is. Okay, so here we see charge defined as the amount of electrons that move through a wire. But we can also use this in the equation we just talked about, right? So if work equals negative Q times E, we just took that equation from the other page and we solved it for W. If I solve it for W, I have to multiply both sides by Q and then also multiply both sides by negative. So that's what we're seeing down here. Okay, so if I have this equation in terms of work, I can actually plug in this idea of what Q is into my equation and get work equals negative NF of E. And this can be a really helpful equation because we can use it to calculate the work done as long as we know what the cell potential is, as well as knowing how many electrons are transferred. And those are pretty simple things to be able to look up. We have been calculating both of those things this whole time. And so if you take those two things and plug them into this equation, you can calculate how much work is done. I'm going to save that example for class. We'll go through and do one of those together. Now, I do want to talk about one last relationship, and that's the relationship of these concepts to G. So remember, when we're talking about G, we're talking about free energy. And the free energy of the system can be used to predict the spontaneity of the system. Okay, so max amount of work that is done is going to be equal to the change in free energy. So we looked at this when we went through that free energy POGL, right? And we looked at how the energy that is available in a system or through a process can be converted into work. And so the free energy change of the system is equal to the maximum amount of work that can be done, as long as no energy is lost to heat, as long as all the energy is actually work, right? As long as all the energy is actually work and none of it is lost as heat, which isn't a real thing, but theoretically, that's the point we're gonna work from. Okay, so if we go back to this equation that we were just talking about on the other page, where work is equal to negative NFE, we can also say that what is also equal to negative NFE. And that would be delta G. So the free energy, we now have another way that we can calculate the free energy. The free energy is equal to negative moles of electrons transferred times Faraday's constant times the cell voltage. Now notice it is the cell voltage standard, so it has to be under standard conditions. As long as we're under standard conditions, you can actually calculate the free energy. And we see another way to be able to verify that our reaction is spontaneous or non-spontaneous. Okay, just a note here that the maximum cell potential is directly related to the free energy difference between reactants and products in the cell. Yes, it is a free energy difference. And remember that the change in free energy is equal to the free energy of the products minus the free energy of the reactants. Or rather, it was this equation. And we see this relationship here as well. So a negative delta G, which is a spontaneous reaction, is a positive E value. So now we can look at delta G to tell if it's spontaneous, delta S of the universe to tell if it's spontaneous, and also the cell potential can also tell us if it's a spontaneous reaction. Okay, so we're going to do these together, but notice that everything you need in order to solve for delta G, for work, determine if it's spontaneous, it's all contained in these half reactions and associated cell potentials that we found on the standard reduction potential chart. So it's all information we already have. We already know how to work with it. We already know where to find it. We're just now using it to find information that is related to the things we've already been talking about. Okay, last relationship that we're going to talk about is cell potential and concentration. So This kind of gets to the idea of work that can be done again and voltage that can be supplied again. And as reactions proceed, what happens to the concentration of the things involved in the reaction? And likewise, what happens to the cell potential? Is the cell potential the same throughout the whole reaction, or does cell potential change? So to start this concept, we're going to talk about if a cell was at equilibrium, what would be the voltage, the cell potential? If a cell was at equilibrium, what would be the cell potential? So I want you to think about that. And we're actually going to come back and explore this concept together. So this is what I want you to think about. As a reaction proceeds forward, think about our cell setup, right? As our reaction proceeds forward, as electrons flow, as the ion of zinc, actually, I think it was the opposite, as solid zinc is turned into the zinc ion. Does the concentration of the zinc ion stay the same, or does it change? Likewise, as the copper ion is turned into solid copper, does the concentration of the copper ion change, or does it stay the same? And as these things happen, what about the voltage? Is that cell potential going to be the same throughout the whole process, or will the cell potential change? When we hit equilibrium with our reaction, what is the cell potential then? So think through these concepts, and we're going to do a little bit of an exploration through these concepts together. All right, for the rest of the time, I want to just talk about application. Electrochem is so applicable. It reaches us in so many areas of our life. So let's kind of walk through some of these scenarios where we might experience electrochem in our lives. First of all, corrosion. Corrosion is going to be a redox reaction. Corrosion is the oxidation of metals, and the oxidation of metals occurs via oxygen. Oxygen is going to oxidize the metals. In some case, this is going to happen with the oxygen that we find in the air. Sometimes it's going to happen with the oxygen that we find in water. In certain situations, this is called rusting, especially when it happens with iron. And notice that the iron actually goes from being solid iron to iron as an ion. But oftentimes that iron doesn't float around dissolved as an ion. It will if there's water present, but a lot of times it actually turns into a solid or a hydrate. And if it's solid, it often becomes a very flaky solid, and it'll break off, and you can kind of rub it off. And it's really fun to do, and your parents get super upset with you when you do that to rust spots on the car. Some metals are so reactive. They're so easily oxidized by oxygen that as soon as they touch the air, they will form a protective layer. And this actually happens with aluminum. When you buy aluminum foil and you roll it out and you have this sheet of aluminum foil that you're about to bake your cookies on, you're not actually setting your cookies on aluminum, because that aluminum is so highly reactive with oxygen that as soon as that aluminum is exposed to oxygen, it actually forms an oxidized layer on the top and probably the bottom of the sheet. So there is aluminum in the middle. However, what your cookies are actually sitting on is aluminum oxide. And aluminum oxide is a very different compound than iron oxide, iron 3 oxide, iron 2 oxide. aluminum oxide will actually stay on the aluminum foil and act as a protective layer, so none of the rest of the aluminum inside there will oxidize. So some metals will do this and some metals will not. And the compound that gets formed with that oxygen looks very different depending on what metal we're talking about. Galvanizing metals is another redox process. So what happens when you galvanize a metal is you coat a metal that reacts very quickly with oxygen with a metal that reacts even faster with oxygen. So notice here we have iron metal on the bottom, but the iron is actually covered with a layer of zinc. And so if oxygen comes in contact with both of them at the same time, zinc is more easily oxidized than iron, and so zinc will react. Iron won't actually react until the oxygen can contact the iron without also contacting the zinc. And so we coat things with zinc, and the zinc actually kind of gets sacrificed for the sake of protecting the iron. And actually, in terms of protecting other metals, sometimes we call it galvanizing when you actually coat the metal with a layer of another metal. But sometimes that other metal is just attached. So notice here that we have a whole thing of magnesium, and it's attached through a wire to a pipe. So magnesium is very easily oxidized, and when something contacts this pipe, like water or oxygen, and tries to steal electrons, the electrons will actually come from the magnesium through the wire down the pipe and actually contact whatever is trying to steal electrons from the metal. Oh, I guess it would actually gain electrons because reduction is gain. Okay, so go the opposite direction. But in any case, magnesium is attached there to be this electron sink, and we actually call it a sacrificial anode. Magnesium is placed in there to be that electron sink so that the pipe is not, and then magnesium is oxidized instead of the pipe, and the pipe is protected. Okay, batteries are a huge application of redox reactions, and I'm laughing because it's probably the first thing that we should acknowledge as an application of redox reaction. So if you break down a battery, all a battery is this half cell system with two half cells paired together. And as we look at the anatomy of this battery here, you can see that. Notice that we have an insulator here at the top so that nothing else is actually gets involved with this reaction. We have a graphite rod, and this graphite rod is going to act as the cathode, which is reduced. We have this manganese oxide and carbon black paste in here. We have a couple salts that are layered in here to be our electrolytes. And then we have zinc here as our anode that's going to get oxidized. And so we have this complete half cell system just contained in something convenient to transport, convenient to plug in, just a little convenient little container. And you can see the reaction at the top. And this would be considered a dry cell battery because everything, including the salts, the two metals, or the anode and cathode, everything is in solid or semi-solid form. Notice that the salts are in this like paste form, so the ions can still move through the paste. Okay, there's also alkaline batteries. but they have similar parts to them. Notice you have an anode cap up here. You have a cathode at the bottom. You have, again, parts of the anode and parts of this salt paste. And then you have a couple other parts to your battery that just kind of keeps it all separated, keeps it all insulated, enables it to connect to the different parts of a circuit when you plug it in. But again, it's just a redox reaction, just like we have been looking at, that can be separated into the two half cells. Lead storage batteries are the same. They have an anode, they have a cathode, they have an overall reaction. Now, lead storage batteries, the anode is lead, and this reaction has to happen in an acidic environment, and the acid that's present is hydrochloric acid. And so lead batteries or car batteries can be especially dangerous because they contain lead, they contain hydrochloric acid, or sulfuric acid, sorry. They contain sulfuric acid. So they have to be taken care of. They have to be disposed of properly. Also, what you're going to get with a car battery is that, notice that this like anode and cathode together actually don't produce a whole lot of voltage. Notice, like, think of a 9-volt battery. A 9-volt battery is something you plug into your fire detector, right? Well, this is not even a 9-volt. But a car battery usually is around 12 volts. So how do they get from this voltage to 12? Let's see if I have a picture of this. So they actually put a bunch of cells, they connect a bunch of cells together. So if each cell generates about 2 volts and they connect 6 cells together, then they can get a 12-volt battery. So a car battery, not only does it have lead inside, not only does it have sulfuric acid inside. Notice that sulfuric acid here is a liquid that sloshes around inside. But it also has it's basically 6 batteries all strung together, giving one amount of voltage. And so it comes with quite a punch, and you never want to touch both electrodes at the same time, because these 12 volts will go across your heart, and that is a 911 situation that you don't want to get yourself into. Okay, fuel cells. This is a lot of research has been done around fuel cells, because fuel cells, if you look at the anode and the cathode here, notice it really just uses hydrogen and oxygen, and the product is water. So if we could run batteries with hydrogen and oxygen where the product is water, that would be much, much better than using lead, sulfuric acid, a whole bunch of metals, a whole bunch of salts that eventually get disposed of, right? So fuel cells are really attractive energy option that a lot of research is being done on right now. The tricky part is, let's say we put a fuel cell into your car, right? Notice what is going to have to be stored in your car. You're going to have to store tanks of hydrogen next to tanks of oxygen in your car. The Hindenburg was filled with hydrogen, right? And it went up in flames. We don't want cars driving on the road that are basically little Hindenburg bombs, right? That's the dangerous part. We would love to produce energy with the byproduct of water. That'd be excellent. But it has to be safe and doable at the same time. So if you become if you go into engineering or chemical engineering, and you go into the energy sector, perhaps you will figure out how to make fuel cells functional. Also, taking sodium chloride and running it backwards, that is an example of an electrolytic cell. Why would you want to do this? Well, perhaps you want chlorine gas. Chlorine gas is stored and used to sanitize things. It used to be widely used at like water treatment plants. But chlorine gas is really toxic, really dangerous to transport and store. And so people and companies are moving away from using chlorine gas, and they're moving towards using things like ultraviolet light for sanitizing instead. So some places still use chlorine gas. Our very own McMinnville Aquatic Center uses huge tanks of chlorine gas in order to sanitize our pool, but our wastewater treatment plant does not store chlorine gas anymore on site. They have moved into ultraviolet light sanitizing instead. But if you wanted to produce solid sodium or solid chlorine, that's not a spontaneous reaction. You have to put energy in. Notice we have a battery here, and the reaction is basically run backwards in order to obtain these products. Same thing with the electrolysis of water. If you wanted to pull apart water and collect the oxygen and hydrogen gas, again, that is a electrolytic cell. You need a battery. You need to pump electricity in order to run that not spontaneous reaction backwards, right? This reaction, as it's written at the bottom, is a non-spontaneous reaction. So in order to run it in that direction, we need an input of energy. But again, you can just see there's an anode, there's a cathode. In this one, again, you need some type of salt like sulfuric acid. We actually have a device in our chemistry classroom that we can use to do exactly this, and we acidify it with sulfuric acid. Same thing with sodium bromide. I'm not exactly sure why you would want bromine or sodium for that matter, although it is fun to watch sodium in water. But again, another example of a reaction that you would need electrolysis to run in a non-spontaneous direction. Okay, lastly, quantitative electrolysis. Okay, so I'm going to cover this concept kind of quickly because it is stoichiometry, and then we can do a couple practice problems together. So it is stoichiometry. You have to take some of these conversion factors that we have talked about, and then when you're doing these problems, you really just want to play with the units and line up the units until you have reduced them out to get the thing that you want. The one formula you have to know, again, we're dipping into physics here, is charge. This is that Q. We used a lowercase q earlier. Charge is going to be equal to the current in amps times time. Okay, so you need this equation, and then you also need that Faraday's concept, that Faraday's constant that we talked about earlier. But if you use these things, then you can actually figure out how many grams or liters of the product it's going to take or make. If you know what the current is, and you know how much time the cell runs for. So for example, if you want to know how much mass of aluminum can be produced if you run a cell for 8 minutes using a current of 100 amps through a molten mixture of aluminum oxide. So we're using electrolysis in order to split aluminum oxide into its components, right? So we're going to start with the formula that you saw on the other page, where we take charge is equal to our current times our time. So if we take our current times our time, 100 amps times 8 minutes, we're going to get out what an amp minute, right? So one more thing you need to know, 1 amp is going to be equal to 1 coulomb per second. So again, we have another conversion factor that you would need in order to convert this. Okay, so we need to convert minutes into seconds. Actually, it's right here. So we convert minutes into seconds, and then this right here is our conversion between seconds, coulombs, and amps. So if I were writing this out, I would go 60 seconds per 1 minute times, and then now I'm going to convert the amps. 1 amp per 1 coulomb second. There we go. Okay, so now basically minutes reduce, amps reduce, seconds reduce. Now I have this in terms of coulombs. And here I dip into Faraday's constant. So I can use Faraday's constant to get out of coulombs, 96500 coulombs. Notice they round it, is equal to 1 mole of electrons. And if I know how many moles of electrons per aluminum, I can get to mass of aluminum. So now I'm going to go 3 moles of electrons per 1 mole of aluminum. And then 1 mole of aluminum on the periodic table is equal to 26.98 grams of aluminum. So it's just a giant stoichiometry problem, right? We did a couple conversions. We did minutes into seconds. We did amps into coulomb seconds. And those two together got us into coulombs. From coulombs, we can get into moles of electrons using Faraday's constant. From moles of electrons, we can get into moles of our atom using the reaction. And from moles of our atom, we can get into mass using the periodic table. So a bunch of these we already know, right? We're comfortable using the periodic table. We're comfortable using the reaction. We're comfortable going minutes to seconds. Two are new to us. So this conversion of coulombs to moles of electrons using Faraday's constant, that would be a new one. And this conversion of amps to coulomb seconds, that's going to be a new conversion factor too. A lot of these conversion factors are on your reference sheet. It would be worth going right now to figure out which ones are on your reference sheet. I gave you one of these to practice in your homework. We can go through another one as well if you want to practice together. I think once you work through this a couple times, though, you're going to feel really comfortable with it just because it is purely stoichiometry. All right, so lots of concepts today. Lots of dipping between physics and chemistry. Let's do some practice together. Let me know what questions you have. I'll see you in class.